So these are the problems from section 8.3 that people wanted to see. So the first one was problem number 3. And so in number 3, it asks for the integral of the square root of 25 minus t squared dt. So the first thing to notice is I can't do a u substitution because if I tried to make it the stuff underneath the square root, I wouldn't have a 2t to plug in. So we're going to end up doing a trig substitution here. So we're going to let t be equal to 5 sine t, which means dt is going to be equal to 5 cosine t dt. And then if I figure out the pieces I need, I have the dt, but I'm going to need a 25 minus t squared, square root of that. So it's going to be a square root of 25 minus 5 sine t squared. So it's going to end up being the square root of 25 minus 25 sine squared t. So I could factor out a 25. So 25 times 1 minus sine squared t. And 1 minus sine squared t is cosine squared t. So we have 25 cosine squared t, or 5 cosine t. I'm also going to eventually need that triangle, so I might as well look at it now. So t is equal to 5 sine t. So if I divide both sides by 5, the sine of t is equal to t over 5. And so I can draw, let me put this up here so I don't accidentally move a page. So I can draw a triangle here. So here's t. So the sine is the opposite, so t over the hypotenuse 5, and then if you use Pythagorean theorem, this would come out to be 25 minus t squared. So my original integral here is going to end up being equal to the integral. So the square root part is 5 cosine t, and then the dt part is 5 sine t. Cosine t dt. And so in this case, we end up with 25 times the integral of cosine squared t dt. And to integrate cosine squared t, we're going to have to use the half angle identity. So 25, the integral of 1 plus cosine of 2t all over 2 dt. I could factor that 2 out. So 25 over 2, the integral of 1 plus the cosine of 2t dt. And I really should have used, instead of t's, thetas here, because I usually use a letter different. I usually use x equals, 5 sine theta, or x equals 5 sine t. But I'm keeping it the way I did it in the solutions. So in this case, we end up with 25 over 2. And when I integrate this, I get theta plus 1/2 the sine of 2t plus c. And I need to read these values off of the triangle, but I don't have the angle 2t in my triangle. I have the angle t. So 25 over 2 is going to be, and this should not be a theta. This should be, I'm used to making these thetas, but since I did everything in terms of t. So t plus 1/2 times 2 sine t cosine t plus c. So this is going to be 25 over 2 times t plus 2 sine t cosine t plus c. And if I plug in, so 25 over 2, and this is going to be the inverse sine of t over 5. That's how I'm going to get back to t. Plus 2, the sine is t over 5. The cosine is the square root of 25 minus t squared over 5 plus c. So that's the first one. And yeah, my using t in 2 places is kind of a little problematic. So if we look at the next one people wanted to see, which was number 4. And so 4 asks for the integral of the square root of y squared minus 49 all over y dy. So in this case, again, a regular u substitution wouldn't work out. So if I do trig substitution, we're going to let y be equal to 7 secant theta, which means dy is going to be 7 secant theta tangent theta d theta. And then I'm going to need the square root of y squared minus 49. So it's going to be the square root of 7 secant theta squared minus 49, which will be the square root of 49 secant squared theta minus 49. I can factor out the 49. So 49 times secant squared theta minus 1. Which is going to end up being the square root of 49 times tangent squared theta, which is going to be 7 tangent theta. And again, I can use this original stuff, y equals 7 secant theta, divide both sides by 7. So the secant of theta is equal to y over 7, and I can draw a triangle from that. So here's theta. Secant is hypotenuse y over the adjacent 7, and then if you use Pythagorean theorem, you would find that this side here is y squared minus 49. And so now if I plug into my integral, the square root turned into 7 tangent theta, the y is 7 secant theta, and then the dy is 7 secant theta tangent theta d theta. So the secants would cancel, the 7s cancel, and so I'm left with, I can factor the 7 out. I have 2 tangents on the top, so I have tangent squared theta d theta. And then I can't integrate tangent squared, but I can replace tangent squared with secant squared theta minus 1. And d theta, and I can actually integrate both of those. So this is going to be 7. The integral of secant squared is tangent theta, so 7 tangent theta minus theta plus c. And so again, 7 tangent theta I can read off my triangle, so it's the square root of y squared minus 49 all over 7 minus. So again, here I know that the secant of theta is equal to y over 7, and that means that theta is going to be the inverse secant of y over 7 plus c. So not too terrible. So if we look at the next one, the next one people wanted was number 7. So this one gave us the integral from 0 to the square root of 3 over 2. 4, or root 3 over 2. Oops, let me undo that. So it's root 3 all over 2 of 4x squared dx divided by 1 minus x squared to the 3 halves. So again, if you try to do substitution, it's not going to work out. So we're going to do trig substitution here. So x is just going to be equal to a sine theta. In this case, a is a 1, so it's just going to be the sine of theta, which means that dx is just going to be cosine theta d theta. And if I look at 1 minus x squared to the 3 halves, that's going to end up being 1 minus sine squared theta to the 3 halves power, which is going to be cosine squared theta to the 3 halves power. So remember, the half part is taking a square root, and we're to have it squared. So in the end, this would just come out to be cosine cubed theta. You can also think about 2 times 3 halves is just 3. We're going to use this part here to draw our triangle. So x is equal to sine theta, and you can think of it as x over 1. So remember, here's theta, sine is opposite x over hypotenuse 1. If you did Pythagorean theorem, this side would come out to be square root of 1 minus x squared. And so now if I plug in, I'm not going to worry about the limits of integration yet. We'll wait till we get all the way at the very bottom, and then we'll take care of them. So we're going to look at the integral of 4. X is sine theta, so x squared is going to be sine squared theta divided by 1 minus x squared to the 3/2. That's cosine cubed theta. And then dx is now cosine theta d theta. And so in this case, one of these cubes would cancel with that cosine. So I can factor the 4 out in front. I have 4 sine squared theta over cosine squared theta d theta. And so this is going to be 4 times the integral of, so sine squared over cosine squared is tangent squared. So tangent squared theta d theta. And then if I use the identity, that tangent squared theta is secant squared theta minus 1 d theta. You're going to end up with 4 times the integral of secant squared is tangent theta minus theta. I'm not going to have that plus c. Remember, I'm using limits of integration, but we want to remember their x values. So it's x equals 0 to x equals root 3 over 2. So this is going to be 4. I'm going to read the tangent off the graph. So x over the square root of 1 minus x squared minus theta, which is going to end up being the inverse sine of x, all evaluated from 0 to root 3 over 2. So all I have left to do is to plug in. So we have 4. When I plug in here, I get root 3 over 2 divided by the square root of 1 minus root 3 over 2 squared minus the inverse sine of root 3 over 2 minus 4 times 0 divided by square root of 1 minus 0 squared minus the inverse sine of 0. Okay, so root 3 over 2 squared, this part here is going to end up being 3/4. 1 minus 3/4 is 1/4. So this first part here we have 4. I have cube root or square root of 3/2 divided by the square root of 1/4 minus the inverse sine of root 3 over 2 is pi over 3. And then minus 4 times, this first one's going to be 0. The inverse sine of 0 is 0. And then all I have left to do is kind of finish this first part here. So we're going to have 4 times, this is going to be root 3 over 2 divided by 1/2 when I take the square root, minus pi over 3. So it's going to be 4 times root 3 minus pi over 3. And you could leave the answer like that. That's totally fine. Okay, so people also want to see 8. So the integral, 8 is the integral of 8 dx over 4x squared plus 1 squared. So again, if you try doing trig substitution, it's not going to work out. The thing we want to notice here is that this is the integral of 8 dx over, we can think of this as 2x squared plus 1, all quantity squared. So rather than let x equal the tangent of theta, we're going to end up having 2x be equal to the tangent of theta. Or if we solve for x, x is going to be 1/2 the tangent of theta. And so in this case, then that means that dx is going to be 1/2 secant squared theta d theta. And if I look at 4x squared plus 1 squared, that's going to end up being, so x is 1/2 tangent theta. So this is going to be 4 times 1/2 tangent theta squared plus 1 all squared. So this is going to end up being 4 times 1/4 tangent squared theta plus 1 squared, or the 4's are going to cancel out. So we end up with tangent squared theta plus 1 squared. Tangent squared theta plus 1 is secant squared theta. So we have secant squared theta squared, which is going to be secant to the 4th theta. And then again, this 2x tangent theta is going to make our triangle. So 2x is equal to the tangent of theta. So you can think of that as 2x over 1. So in terms of my triangle, tangent opposite 2x adjacent 1, which makes this square root of 4x squared plus 1 if you do Pythagorean theorem. So now we just have to plug all the pieces in. So I have the integral of 8 dx is 1/2 secant squared theta d theta. And then on the bottom, I just have a secant to the 4th theta. So in this case, the 8 and the 2 are going to cancel, leaving with a 4. These two secant squareds cancel out 2 of these. And so we're left with 4 times the integral of 1 over secant squared theta d theta. But secant squared theta, 1 over secant squared theta is just the cosine squared theta. So 4 times the integral of the cosine squared theta d theta. And then to integrate cosine squared theta, I have to use the half angle identity. So I have 4 times the integral of 1 plus the cosine of 2 theta over 2 d theta. So I could factor out that 2, or this 2. Think of it, this 2 and the 4 cancel. So I'm left with 2 times the integral of 1 plus the cosine of 2 theta d theta. And so if I integrate each of those pieces, I have 2 times the integral of 1 is theta. The integral of cosine of 2 theta is 1/2 sine 2 theta plus c. And remember, we have to, and I still have here theta. I'm not going to be able to figure out sine of 2 theta off of the triangle. So it's going to be plus theta plus 1/2 times 2 sine theta cosine theta plus c. So my 2's would cancel here, which I think I forgot to do in the solutions. I think I off by a factor of 2. Or no, I guess I do it, but yeah, it's fine. So this is going to become 2 times theta plus sine theta cosine theta plus c. So, and I'm just going to move this up here a little bit so I have a little more room. So again, back to here to figure out what theta is. Theta is going to be the inverse tangent of 2x. So we have 2 tangent inverse of 2x plus the sine is going to be 2x over the square root of 4x squared plus 1 times the cosine, which is 1 over the square root of 4x squared plus 1 plus c. And I know I took it one step further on the solutions, but you can stop there. Okay, so there were 2 more people wanted to see. One is number 9. So number 9 asks for the integral from 0 to the natural log of 4 of e to the t dt divided by the square root of e to the 2t plus 9. So the first thing to notice here is that you can, okay, so as I was saying, the first thing to notice is if you try to do a u substitution on the bottom, you're going to get stuck because you're going to need an e to the 2t for your du, and you don't have that. So this is reminiscent of being a trig substitution problem, but the thing is, to be trig substitution, you really need to have x equals, or you need to have x squared or something squared plus the number, which we do, but the thing we have squared is e to the t. So the thing to think about is that this is the same as the integral from 0 to natural log of 4 of e to the t dt all over the square root of e to the t squared plus 9. So the first thing I'm going to do is I'm just going to do a u substitution. So if we let u be equal to e to the t, du is going to equal e to the t dt. And then if I also change the limits of integration, when t is equal to the natural log of 4, u is going to be e to the natural log of 4, which is just 4. And if when t is equal to 0, u is going to be e to the 0, and e to the 0 is just 1. So I made the problem a little bit nicer in that now it should just be the integral from 1 to 4 of du all over the square root of u squared plus 9. And so now I'm in a point where I can do trig substitution. So if we let u be equal to 3 tangent theta, du is going to be 3 secant squared theta d theta. And then I also need to figure out the square root of u squared plus 9. So that's going to end up being the square root of 3 tangent theta squared plus 9, which is going to be the square root of 9 tangent squared theta plus 9. If we factor out a 9 times tangent squared theta plus 1. So square root of 9 secant squared theta, or 3 secant theta. And again, I'm going to use this u part to make a triangle. So if u is equal to 3 tangent theta, this is telling me that the tangent of theta is equal to u divided by 3, if I divide both sides by 3. And so in terms of a triangle, here's theta, opposite u, adjacent 3. Using Pythagorean theorem, this ends up being u squared plus 9. Okay, so I'm going to slide over because I've already moved away from t's into u's and I changed the limits, so we're okay. So this integral is going to become, I'm just going to worry about the integral. We'll take care of those u limits at the end. So du is 3 secant squared theta d theta, and then the square root is 3 secant theta. So my 3's would cancel. This secant is going to cancel this one. So we're just left with the integral of the secant of theta d theta. And that's one of the integrals that I have on that sheet for you. So this is going to be the natural log, the absolute value of secant theta plus, secant theta plus tangent theta. And then remember, we're evaluating it, but those 1 and 4 are u limits. So from u equals 1 to u equals 4. And so I have to read off of the triangle what the secant of theta is. So secant is going to be the hypotenuse, so u squared plus 9 divided by the adjacent, so divided by 3. And then we have the tangent is the opposite u over the adjacent 3. And then we're evaluating this from 1 to 4. So we're going to have the natural log, absolute value of, if I plug in here, I'm going to have 4 squared is 16 plus 9 all over 3 plus 4/3 minus, I'm out of room here, the natural log of the square root of 1 plus 9 over 3 plus 1/3. And I can clean this up just a little bit. So 16 plus 3, if 16 plus 9 is 25, and the square root of 25 is 5. So we have the natural log of 5/3 plus 4/3 minus the natural log of the square root of 10/3 plus 1/3. And I could just clean this up a little bit. So this is going to be the natural log. So 5 plus 4 is 9, 9/3, but 9/3 is just 3. So this is just the natural log of 3. Minus, there's not much I can do here, so it's just square root of 10/3. And I guess I could write it as square root of 10 plus 1 all over 3. So not too terrible. But it did take that little bit of trick at the beginning that you had to see that you could rewrite that first thing as use substitution on that first problem. All right, so the last one here, 10, and problem 10 is one of these initial value problems. So we have x squared plus 4 dy dx equals 3, and y is equal y, of 2 equals 0. Okay, so the first thing, we did do a problem, I believe, like this in class, and you kind of want to think about, basically, I'm trying to separate out the variables. So we can think of that dy dx as kind of two pieces of variables. So if I multiplied both sides by dx, on the left side, I'd just be left with x squared plus 4 quantity times dy. And on the right side, I'd have 3 dx. And now if I divide both sides by x squared plus 4, I'm going to end up with dy is equal to 3 over x squared plus 4 dx. And if I end up doing this, so now if I integrate both of these sides, the integral of dy is just y, and then I have to figure out what this integral is. So 3 integral of x squared plus 4 dx. And to do that, I'm going to do trig substitution. So we're going to let x be equal to 2 tangent theta. So dx is going to be equal to 2 secant squared theta d theta. And then x squared plus 4 is going to be 2 tangent theta squared plus 4, or 4 tangent squared theta plus 4, which is going to be 4 times tangent squared theta plus 1, which is going to be 4 secant squared theta. And so if I plug in here, y is going to be equal to 3 over x squared plus 4 is 4 secant squared theta, and then dx is 2 secant squared theta d theta. So the 4 and the 2 would cancel. I'm just left with 2 here. The secant squareds would cancel. And so really all I have is y is equal to 3 halves times the integral of d theta. And so if you integrate d theta, you end up with y is equal to 3 halves theta plus c. And if I use, I never drew my triangle, but from here, right, I just need to know what theta is. So if x is equal to 2 tangent theta, divide both sides by 2, the tangent of theta is equal to x over 2, and I can use that to draw my triangle. But in this case, I don't even have to draw the whole triangle because all I need is theta. So theta is going to be the inverse tangent of x over 2 plus c. And so that's normally where we would stop, but since this is one of those initial value problems, if you look way back at the beginning, we knew that y of 2 equals 0. So that's what we're going to use that information now. So we know that y of 2 equals 0. So that means when I plug 2 in for x, I should get 0 for y. So doing that, that means 0 is equal to 3 halves, the inverse tangent of 2 over 2 plus c. So 0 is equal to 3 halves, the inverse tangent of 1. And the inverse tangent of 1 is pi over 4. So 0 is going to be equal to 3 halves times pi over 4 plus c. Or 0 is equal to 3 pi over 8 plus c, which means c is equal to minus 3 pi over 8. And now I can go back and plug back into my problem. So y is equal to 3 halves, the inverse tangent of x over 2 minus 3 pi over 8. And so we had to find the c just because it was this initial value problem.